All right, welcome everyone. Let's get started. I've just collected the last homework 2B, and I wanted to go over a few points related to what I was handing back, the assignment that I've just handed back to you. First of all, the grader on a few papers has indicated if your neatness wasn't good enough, and in a future assignment, if it wasn't clearer and easier for the grader to find your solution, then points would be deducted or the assignment would just be returned to you. And so you need to keep in mind that it's your responsibility to provide a clear solution, and it's not the grader's responsibility to try and figure out what you did. And so if it's just a confusing, disorganized jumble, the grader really doesn't have to spend a lot of time trying to figure out a sloppy solution. And so please be professional and clear as you're doing your solution. And by the way, you should know that I'm not grading your homework assignments. And so, if there's points deducted, you can't immediately come to me and say, why did you take off these points? Because I'm not the one who graded it. I'm happy to look at the assignment with you. If you'd like to come by my office during office hours, we can definitely look at the solution, look at your paper, and go over it together to try and help you understand any mistakes that you may have made. But coming up to me while I'm getting the lecture ready, I'm not going to be able to answer any questions why you had points deducted, mainly because I haven't seen your paper before. So just keep that in mind. Some smaller issues, please staple your papers together. Don't use a plastic sleeve. Don't just fold the papers together. Use an actual paper so that your pages don't get separated. Don't leave like the rough bits of paper on the side, these rough little bits here. It's very annoying and unprofessional. Don't do that. And also, only write on one side of the paper. Don't use both sides of the paper. It's good to conserve trees, but we don't have to be that stingy with paper. So please just write on a single side only. All right, so your next assignment is due on Sunday the 21st. And as you can see, there's a lot of problems in this set. And I'd encourage you to get started early, so that it's not a crush all at once trying to solve those. We're going to go over 5 examples in class today. And so, there's a lot of information that will be in today's lecture that can support you in getting started on that assignment pretty quickly. So what we're talking about today is hydrostatics and pressure transmission. And before we get into that new material, any questions related to the announcements or related to the homework tips that I've just given you? Yeah. Yeah. Will you remind me what that problem is? Is it like the vapor pressure problem? Yes. I don't remember if it's a yes or a no. Yeah. Sorry. If you'd like to stop by my office, we can go over it. But I remember the problem, but I don't remember if they made it a yes or a no. Yeah. Yeah. The quiz is going to include the material that was on homework 2B and homework 2A. All right? So the quiz won't include material from today's class. All right, so let's just review some information related to pressure variation through a fluid. And like I said, we've got a lot of examples to work today, and so this one I'm not going to actually have you do the calculations because we have to sort of speed through some of them so you've got more time to focus on the new ones. But this is just to remind you that the hydrostatic equation can look a couple of different ways. On the left, this is the full version of the hydrostatic equation, and we use it when we're measuring elevation above some datum. So Z is the elevation above a point that we say this is defined as our zero elevation. And so location 1 and location 2 will both be measured from that same point. And if we use the bottom of the tank as the datum, then you can see Z2 would be 15 and Z1 would be 50. But we could use the top of the water as our elevation datum. And then Z1 would be 0 and Z2 would be negative 35. And we'd still get the same answer regardless of what we used as our Z location. Another important point is that if we choose the water surface as our elevation, like a little example like this, we're going to say that P1 is 0. Most typically, we're going to solve problems like this for the rest of the semester usually in gauge. Unless it specifically says absolute pressure, then you assume that the air pressure is 0 and everything starts from there. And so here, if we were doing it as a gauge problem, we'd say P1 is 0, and then we'd be finding P2, which is going to be a positive pressure because we're going down through the fluid. So there's both ways of the solution. So let's just take a look at the PDF of it and see if it makes sense. All right, yeah, this is the one. Okay, so it says that it's water. We have a unit weight of 9810 newtons per cubic meter. I'm using the bottom of the tank as an elevation datum, so that makes Z1 is 50, Z2 is 15. And if we're solving for the gauge pressure, then we say P1 is 0. And if we're solving for the absolute pressure, then we say P1 is 101,325 pascals, and that's the standard atmospheric pressure. Okay, so I've done it two ways. The first way is the full hydrostatic equation where we're substituting in the known elevations once I rearrange to solve and isolate the P2 as the unknown. So here you can see the unit weight, then the pressure head term. And remember that when we rearrange pressure and divide it by the unit weight, we call it pressure head, and it has elevation units of meters. So the pressure divided by unit weight, the units will work out to meters, and that's why we can add it to the Z values, because they also have units of meters. But here, P1 was 0, so it just cancels out entirely. Okay, so here's our pressure in terms of gauge when you are that depth under the water, or the absolute pressure, you're simply adding 101,325 to that. So the abbreviated hydrostatic equation is even a little bit easier because we're just saying what's the change in pressure from the surface down to the point of interest. And we're saying that the pressure at the surface starts off as 0, so all we really need to know is the change. So the change in depth is 35, the change in pressure is going to be 343 kPa. And then same thing with the absolute, just adding 101.325 if it's kilopascals, or if it's pascals, 101,325. So I think you get the idea. Any questions about this illustration, just to remind you what's going on with the hydrostatic equation? You'll have another reminder of the hydrostatic equation when we take that quiz on Tuesday. All right? Yeah. Yeah. Here?
Yeah.
Okay.
Why do you take 50?
Pardon me?
Why do you take Z2
As 50?
50?
Oh, 15. Because I'm measuring, I'm saying that here the bottom of the tank is Z0. And if you look at the dimensions, it says it's 50 to the top and then 35 from the top down to 2. And so 50 minus 35, that means that the elevation from this line, from the datum, up to 2 is 15 meters. Mm-hmm. Here? Delta H is the difference from the surface to wherever you're trying to find the pressure. And in this one, we're trying to find the pressure at 2. Other questions? Well, not that example, but the topic of the hydrostatic equation is on the quiz. You know, that's the focus of Chapter 2. All right, so another application of the hydrostatic equation is what if you have two different liquids? Because what we've been doing so far is you're going down and you're going through down through just one fluid. But in this one, we've got oil layer on top of a water layer. And I'd like you to solve this one. I'm actually going to pause the recording and stop talking so that you can try and figure this one out. Let's just talk through it together and then let you solve it. First of all, I'm going to bring this up so we can do the dimensions a little bit easier. Okay, this is oil. And what do we know about the fluid properties? We know that S, the specific gravity, is 0.75. And then here we know that this is water, and the properties of it, it's at 10 degrees Celsius. Well, if you look up in the back of the book, the unit weight for water at 10 degrees Celsius, it's the same as our default unit weight. It's the 9810 newtons per meter cubed. All right? We know that the total liquid level in the tank is 4 meters. So 4 meters is the total amount of liquid, and the oil layer is 1.1 meters. So this is 1.1 meters. I'd like you to tell me the pressure at the bottom of the tank. So what is the pressure down here at the bottom of the tank? And the principle is, the way you solve it, start at the top, go to the interface, find the pressure at the interface, and then go to the bottom. And the reason why you have to do it in 2 steps instead of just 1 step is that when you are applying delta P is delta H times the unit weight, you've got two different liquids. So you go through this using the unit weight of the oil, and then you go through this using the unit weight of the water. Okay? So collaborate with your colleagues on this one, and let's find the pressure at the bottom of the tank. Okay, so over here on the whiteboard, I reminded you how to use S. This is something that we talked about during fluid properties, and so that should be in your mind already, how to find the unit weight of the oil if all you're given is the specific gravity. So the specific gravity is relative to the unit weight of water, or relative to the density of water, depending on what you're trying to find. In our case, we're trying to find the unit weight of oil, so it means it's a ratio. So it's 75% the unit weight of 9810 newtons per meter cubed. And so that's how we find that the unit weight of the oil, in our case, is 7357.5 newtons per meter cubed. Let me bring up the solution for this one. All right. You can see I did the drawing just because having the drawing on your own, I think, is a good habit that will help you avoid mistakes, help you visualize the problem a little better. So the first thing I did was took care of my fluid properties, finding the unit weight of the oil. And since we're working this in gauge, that means that the pressure at the surface is 0. So you can see that I've labeled locations. Location 1 is at the surface where I know something. I'm starting with a known, working towards the unknown. The known location is the interface of the air and the water. So the pressure of the air is 0. That means that the pressure of the oil that's touching the air is also 0. And then as I go down through the oil, the pressure is accumulating and increasing. So location 2 is the interface between the two liquids, and then location 3 is at the bottom of the tank where I'm trying to find the pressure. So I do it in a progressive way. P1 is 0. P2 is P1 plus the delta P. The delta P is the change in pressure that occurs as we go down through a distance of 1.1 meters of oil. And so the increase in pressure is 8093 newtons per meter squared, and that's added to the P1 of 0 pressure. So that's the pressure at the interface of the liquid. And so if we zoom in, like with a microscope, at the interface of those two liquids, the oil pressure and the water pressure are exactly the same where the two liquids are touching. But then if you go down even just a little bit through the water, then the pressure starts to accumulate again. And in this case, the distance we go down through the water is 2.9 meters, because we do 4 minus 1.1, and that gives us the distance, the vertical distance between location 1 and location 2. Remember, you can go sideways through a liquid and the pressure doesn't change at all. It's only when you're going down that the pressure increases, or if you go up through the liquid, the pressure is decreasing. Okay, so ultimately, here's the answer, 36.5 kPa.
So does this repeat something like this and solve the equation?
Well, there's maybe a few equations you need to memorize. For example, I would expect you to memorize how to use the unit weight. And so, whether you know what the definition of S is or whether you consider this memorizing an equation, this is something that maybe I wouldn't give you. I wouldn't define S for you. But I would provide the hydrostatic equation at the bottom of the page on a quiz. Questions about the example before we move on? That's right. Thanks for asking. Yes, this is the gauge pressure. And if we wanted to know the absolute pressure, then we'd just add 101,325 to that. Good question. All right. All right, this is some interesting stuff. I'm excited we get to talk about this today. So maybe you've seen a car lift before. When you've taken your car into the agency for maintenance, they can lift it up off of the ground, and oftentimes the way they do that is with the hydraulic system. And so what you can imagine is that over here is some sort of an air compressor. It's taking atmospheric air and it's forcing it into a small space. The small space is this tube that connects the compressor to a greater reservoir full of air. And now this air is pressurized, and what it's doing, because it's pressurized, is it's pushing down on the liquid that's inside the hydraulic system. So it's oil. So the air is pushing down on the oil like that, and so there's pressure, and as we go down, the pressure is getting even a little bigger. As we go sideways, the pressure is the same. It's not doing anything. We're going up. The pressure is decreasing just a little. So assume that these are about the same elevation. You know, if we were to count the pixels on the screen, it kind of looks like this line's a little bit higher. Well, let's just say those two elevations are the same. So what it means is that the pressure down of the air pushing on the oil is the same as the pressure up the oil is pushing on the face of this cylinder. This is a circular cylinder here. So if I was trying to draw that in 3 dimensions, it would look like that. You know, it's a circular cylinder, and the oil is pushing up on that face. So does everybody sort of visualize what's happening with this? And because the pressure of the oil is pushing up, then that's what gives this the ability to lift something heavy, like a car. And so in this instance, we could calculate how heavy the car is by knowing 2 things: the pressure inside the system, and then also the area of the cylinder. Now, I mean, you maybe wouldn't necessarily know that, except for that in a problem statement where it says, for example, what is the force of the system, and they give you this diameter. We're told the diameter of this metal cylinder that's supporting the weight of the system. Then you could think, with the diameter, I can calculate the cross-sectional area. And then you start thinking about the units, and force, how does that relate to pressure and area? Well, pressure has units of newtons per meter squared, and area has units of square meters. And so if you multiply those 2 things together, you're going to end up with units of newtons, which is a force. So in pressure transmission, one of the first things we're going to look at is how you can actually lift something very heavy, and all you need to do is change the area that the pressure is acting on. You can do 2 things, actually. If you want a big F, so if you want the capacity to lift a very heavy truck, for example, you can either have a high pressure, a big area, or some combination of the 2. All right. So we've got some specific values here. We've got a diameter of the cylinder is 25 centimeters, and that works out to an area of 0.04909. I did that calculation just to save the time.
So, Professor, the maximum height the lift can go to is the same level as the oil in this chamber?
That's a good question, yeah. You know, how high could this lift go? I think the maximum height this lift could go is if we give it more pressure, then this is going to go up, and this liquid level is going down, right? Because there's only a certain amount of oil in this system. So if the lift goes up 1 centimeter, then this level goes down. Well, they're different diameters, so it would depend on how much oil is in the system, really.
The oil, the other chamber, there.
Here?
No, the other one.
This one.
When oil goes up, the pressure.
When the pressure goes up, then it will lift it higher.
No, but when the oil level goes high, the pressure will decrease.
As you're going up through oil, pressure is decreasing.
Wouldn't that like affect the lift?
No, because let's look at it this way. Same system. Here is the reservoir. Here's the lift. All right. So it's connected like this. So let's say it's in equilibrium, just as it is now in the picture. Here is the air, here is the oil, and then this is metal, right? So right now it's stable. If we want to lift it higher, then we put in more pressure. Okay, so when we put in more pressure, then this will begin to go up. But when does it stop going up, is my question. When would, if we just add a little bit more pressure, would it go up forever, or when would it stop going up? When there's some sort of a balance, right? When it's in equilibrium. And so let's say we put in another 5 kPa of pressure. So it's going to go up some extra distance, and the extra distance it goes up is because of delta P is delta H times gamma. And so whatever this is an oil, then the change in pressure, we add more air and we increase the pressure a certain amount, that's going to increase the delta H by a certain amount. So it will come into equilibrium eventually. Now, you know, the original question was, well, the pressure is going down. It's just the pressure here and here is the same as it always was. It's just now we go up and the pressure is decreasing until it's in equilibrium with the increased amount of pressure that we added to the system. So that's why it can go up and it can go down. Is if we want it to go lower, then we would decrease the pressure in the head space above the oil. So that's a good question. I'm glad you asked it. Now let's look at the specifics here. Let's find out how heavy is this car. Specifically, this vehicle has a certain weight measured in newtons that we can find out because we know the pressure is 600 kilonewtons per square meter and we know the area. So all we have to do to find the force that's lifting this is multiply those two terms together, pressure times area. Okay, hydraulic jack, compressor. All right, this one. So I've done the little drawing of the system. And you can see in my drawing, I'm reminding myself that what causes this pressure acting up is the pressure in the air pushing down on the liquid. Pressure acts in all directions. It's a scalar, not a vector. And so that's why pushing down with the air can cause the pushing up here is we go down and sideways and then back up again. And these are at the same height, so it's the same amount of pressure. So it's the 600,000 newtons per square meter multiplied by the area of the cylinder. This isn't the area of this tank. It's the area here. You can see I've noted it's the pi d squared divided by 4 is how I got that area. And that works out to 29,000 newtons approximately. And if we divide the force, which is a weight, by G, 9.81, that's about 3,000 kilograms. So that's a heavy car. It's maybe a Mercedes. Mercedes are usually pretty heavy, right? All right. So any questions about pressure transmission? All right. So it gets even more beautiful or more complicated depending on how you look at it. We've already talked about the equilibrium situation. What would happen if we turned the air compressor on? So this is stable with the 600 pressure. So if we turn on the compressor, it puts more air inside that enclosed space, which is what would increase the pressure, and the cylinder on the right would go up until the pressures are all in balance again, until it reaches the new equilibrium of it's a little bit higher, delta H, because of the increased pressure, delta P. All right. This looks like a complicated part, right? But it's a really great illustration. And once you work through this example, then I think the homework will come very naturally to you. So this is another one that I'm going to stop talking and circulate around as you work on this. But I wanted to explain a few of the pieces and how they work before I turn you loose on it. So let's talk about what's happening with this jack. You push down on the handle, and this jack wants to lift something heavy with the big piece on the right. It's amplifying the force in two different ways, mechanically and hydraulically. It's amplifying your force. The first way is you look at the arm of the jack, and you can sort of see that if you push down on the handle, let's draw a little diagram of it. If you push down on the handle here with a certain force, then the force that you'd need to balance that here is going to be much greater. You know, this is a moment, right, where it's 33 centimeters from the edge to where force 1 is applied, and then from force 2, no, we're not calling that force 2. Force 2 is this one. We'll call this the force at B, because location B is where that part connects. So the force at B is only 3 centimeters away. Okay, so the first thing you're going to need to do in this problem is use moment analysis to say, I know the force at 1, and I know the moment distance, and I know the moment distance from the hinge to B, but I want to find what is the force at B. And it's going to be greater than 100 newtons applied here, because we know that this force on the handle is 100 newtons. Okay, so you're going to find the force at B. And if there's a force there, what is it actually doing? We can look at the part, and it's pushing down, right? It's pushing down on the liquid. And so it's a circular part. So here's the same force at B. It's pushing down and it's pressurizing the liquid. So here is a hydraulic fluid inside of this jack. And so when you push down on the handle, it's like suddenly this liquid becomes pressurized because of the force on the handle. So there's a certain force. How do we find the pressure inside of the fluid if we know areas and we know force? What's the formula relating pressure, force, and area? Okay, F equals PA. And so the pressure inside the liquid is F divided by A. Right. So A1 is talking about this circular area here, A1. Okay, so that's where I'm going to stop talking and allow you to start working through the rest of the problems. You follow these steps and you find the pressure in the liquid. Next, I'd like you to find out how much can that jack actually lift. What is F2? And we know the diameter of both this part, and we know the diameter of the other part as well. And of course, you can work with your colleagues on this one. There's no need to be quiet during these examples. Lots of good solutions out there. All right, let's look at this one. Okay, so we start with the handle, right? We want to find out what is FB. So you can see I did my little moment analysis here, and I didn't bother converting from centimeters to meters. You could, but you're going to be dividing centimeters by centimeters when you rearrange this equation for FB. So you can just leave it as is and get that the force upward onto the handle is 1,100 newtons, and so then the equal and opposite reaction is down on that little plug, the plug that's actually touching the hydraulic fluid. So that's 1,100 newtons downward. And then I want to find the area of that part based on the 1.5 centimeter diameter that's given. So I convert that to meters. I guess you could have, in the same way that you could have left this in centimeters, you could do the area in centimeters squared, because eventually you could divide here the area by centimeters squared. But the reason I didn't do that is because I wanted to know the pressure in terms of force newtons per meter squared. That's the more typical way to describe pressure, is newtons per square meter rather than newtons per square centimeter. So this is the pressure at the bottom here it's causing the pressure all the way through the fluid as well. And since these two parts are at the same elevation, this plug and this plug are at the same height, that means that the pressure here is the same as the pressure there. Even though the diameters of the cylinders are different, that doesn't affect the pressure inside the hydraulic fluid. We could have made this 10 centimeters, and the liquid pressure would be the same. All right, so we know the pressure in the liquid. Now I'm taking a look at the fluid itself. So I've got A1 and a calculated A2 over here, and then a little drawing just to show that the pressure is pushing up on that secondary cylinder, and we know the area of that secondary cylinder, calculated that, and so the force it can lift is 12,222 newtons, so approximately 12.2 kilonewtons. That's the load it can lift. What if this was 10 centimeters instead of 5 centimeters? What would happen to this force if we doubled the diameter of that secondary cylinder? It would increase, quadruple. It would be 4 times greater because remember it's pi d squared, right? So you could really lift some heavy things just by making it larger and larger area, and you wouldn't have to push any harder on the handle. So if you want to lift something heavy, the key is a long handle, and then it's better to have a small area on this side because that causes a high pressure. The smaller this is and the bigger this is what amplifies your ability to lift. All right, so now that you've seen this example and worked it and you've got your notes to keep with you, I think you'll have an easy time tackling the homework problems that relate to this same idea. That's why I give you the suggestion to start early on the homework, is because it's fresh in your mind right now. It won't be fresh in your mind Saturday night, after a long weekend. So if you started this today, then you'll really be doing yourself a favor. All right, the last thing we're going to talk about today is just a few minutes to begin envisioning ways to measure pressure. Because until now we've just been saying here is the pressure, just by definition it's a certain amount. But we have instruments we can use, very simple ways of measuring the pressure. And one of the most obvious is something called a piezometer. And consider, what if there is a pipeline, it's maybe buried under the road, just a pipe carrying water, the water is flowing through the pipe, and we wanted to know how much pressure is there at the center of the pipe. One of the very easy ways that we could measure the pressure of liquid in a pipe is just if we poke a hole in the pipe. Now, if that's all we did, then water's going to be spraying everywhere. It would be a disaster. But if we poke a hole in the pipe and we connect it to a tube that goes up some distance, then the liquid level will rise until into the tube, and then eventually it would stop. It would stop rising, assuming that the tube is tall enough to contain all this liquid. If the tube wasn't tall enough, then it's just going to be spraying out. But let's say it's a very, very tall tube. Well, then the water is going to rise until the height of water in that column is in equilibrium with the pressure in the pipe. What equation tells us how high the water will rise due to a certain pressure? All right. Yeah, I'll buy that, because the hydrostatic equation is delta P is the unit weight times delta H, right? This is the equation. Now, the interesting thing about it is it doesn't matter how big this hole is. If it's a small diameter opening or a large diameter opening, it's going to rise to the same level. And so manometry, a manometer is a physical device that's used to measure pressure. Now this particular type of manometer isn't very convenient for a couple of reasons. One of the problems is that a typical water pressure in a city, the pipes that are running through University City, they're carrying a pressure of about 500 kPa. That's a typical pressure. In other words, that's 500,000 newtons per meter squared. So the way we measure the pressure here is we just see how tall is the head that's poking out of this pipe here. And so if the water rises really high, that means you've got a big pressure in the pipe. If it doesn't rise very high, then you could have, little marks on the pipe, and you'd be saying, okay, it's to this level, that means the pressure is a certain amount. So how high would the delta H be for this typical pressure? Well, we could find the delta H is P divided by the unit weight. And if we have 500,000 as our typical pressure, newtons per meter squared, and we're working with a unit weight of 9810 newtons per meter cubed, yeah, it's 50 meters, right? I think about the person who has to measure that, like up on stilts or maybe a really tall ladder, 50 meters in the air. It's just not convenient, right? So there's better devices than this for measuring pressure. You don't see in the middle of the road these gigantic 50-meter tubes going up into the air for people to measure the pressure. But this is the simplest, and so we're going to start talking about measuring pressure with piezometers. And if it's 10 meters, then all you do is you just multiply, divide the, so for 10 meters as our delta H, then the delta P, delta H times gamma, right? So if we wanted to know for a 10-meter head what is the pressure, then we would do this one, very simple. 10 meters of water is the same as 98.1 kPa. All right, so that's your sneak peek at manometry. We're going to do more of that on Tuesday, but before we get to manometry on Tuesday, we're going to have our first quiz. Don't get stressed out about the quiz. If you know the homework, it will come smooth for you. It's a small number of points, and so just come into the quiz feeling relaxed, and everything will be fine. So I'll see you on Tuesday, and hope you have a good day.